So welcome to Manish Kumar channel. So today we are going to discuss about matrix of linear transformation. So in this lecture we show the following. A linear transformation is uniquely determined by its action on a basis, right? And then we will also see how to represent a linear transformation as a matrix. So we now show that if V is an n-dimensional vector space and W be any vector space, then a linear transformation L from V to W is completely determined by its action on the vectors of an ordered basis for V. And regarding the linear transformation, we have already done in the previous video, so I would request you to prefer to see my previous video for linear transformation. So the result, suppose V1, V2, Vn is a basis for V and W1, W2 and vectors in W, then there exists a unique linear transformation L from V to W such that L of Vi is equal to Wi for all I equal to 1 to n. So let us see how to prove this result. So let any V belongs to the vector space V, then since basis of V is given as V1, V2, Vn, so every vector can be uniquely written as a linear combination of the basis vectors. So now I can write V as alpha 1 V1 plus alpha 2 V2 and so on alpha n Vn, where alpha 1, alpha 2, alpha n all are scalars, right, coming from the field. So here we are talking about field uh, V over R, right? Vector space over real field. So this is field. Okay. So now we define a map L from V to W as L operated on V is nothing but alpha 1 W1 plus alpha 2 W2 and so on alpha n Wn, right? Then we can easily show that this map is linear, right? And LVI equal to WI for all I equal to 1 to n. So how do we prove linearity? So assume because we have to prove two properties, L is closed under vector addition and L is closed under scalar multiplication. So let U and V belongs to V, then we can write U as a unique linear combination of basis vector, and V can also be written as a unique combination of basis vector with different scalars. Okay, alpha 1, alpha 2, alpha n, and beta 1, beta 2, beta n. So what about the U plus V? U plus V is also is in B because of the fact that V is vector space. So U plus V can be written as the scalar component sum alpha 1 plus beta 1 into V1, alpha 2, beta 2, V2, and so on. Now we can apply L on both sides. So if you apply L of U plus V can be just nothing but L of alpha 1 plus beta 1 into L of V1 is nothing but your L of V1 is nothing but W1, right? So we are replacing all the transform value with W1, W2, Wn. Now we can expand this and write in the form of alpha 1, alpha 2, and so on, alpha n together, and beta 1, beta 2, beta n on the other side, right? So what we can say that this first alpha 1 combination will be L of U, and second beta combination will be L of V. So it means that L of U plus V is equal to L of U plus L of V. So L is closed under vector addition. Similarly, for any alpha, I can write alpha v can be written as the linear combination of alpha times of alpha 1 w1, alpha 2 w2, and so on, and then this is nothing but alpha times of L of v. So it means that L is linear. Okay, now we need to prove that L of vi equal to wi for all I equal to 1 to n, right? So this is because of the fact that v1 cannot be expressed as the linear combination of basis vector, because v1 is linearly independent. This set, basically this set, v1, v2, and vn is basis, which implies linearly independent and span, right? So since linearly independent, it implies that v1 cannot be written as the linear combination of any remaining vector v2, v3, and so on, vn, right? So this only possibility is v1 can be written as 1 times of v1 plus 0 times of v2 plus and so on 0 times of vn, because of linearly independent property. It means that apply linear transform of v1, and which gives us 1 times of w1 plus 0 times of w2 and so on 0 times of wn, which means v1 L of v1 can be written as only w1. Similarly, L of v2 can be written as w2 and so on wn, right? L of vn can be written as wn. So which means that the basis vector, later we will see these w1, w2, wn are the basis for the given vector space w. It means you have a transformation L, you have a vector space v, and you have a vector space w, right? And if you have a linear transformation from v to w, and this is the set b, right, which is a collection of all the v1, v2, vn, and if you have a collection subset w, right, another basis, let's say b dash, so b dash is nothing but your w1, w2, and so on wn, right? So we will see that basis element map to the basis element, right? And it's unique linear transformation that we will see. Okay, so now L of V1 can be W1, L of V2 can be W2, and so on. L of Vn can be written as Wn. No other possibilities. Okay. Now we have to prove that this linear transformation is unique. Always it is unique, because if you see the previous video, then you can see this basis coordinate change of basis, right? How we are going to change from basis from one place to another place. So coordinatization, if you see the video of coordinatization, then you will find that, okay, because of the basis you are representing, so always you will get unique linear transformation. Okay, so now uniqueness of L. So assume T is another linear transformation from V to W, right? Such that T of Vi equal to Wi. Then what is our claim? We can say that this T is nothing but L only. So since any vector V can be written as a linear combination of the basis vector, right? So T on V, operated on V, can be written as T of this, and T of this, these will be actually your TV1, TV2, because T is linear. So since T of Vi equal to Wi, so we get W1, W2, W3, and so on Wn. And since we have already proved that L of V equal to alpha 1 W1, alpha 2 W2, and so on, so from both equation we can say that T of V equal to T of L of V. So it means L equal to T only. So we cannot find another transformation. So this transformation is unique. Okay. Now let us look one example. Linear transformation is determined by its action on basis. So L is a linear transformation such that L from R2 to R2, and this is also known as operator because V is equal to W here. V is equal to W, right? So V and W are equal, then you can see that this is an operator. Okay, range is equal to the codomain, right? So what happened is here is so L on basis vector it is given 1 0 equal to 2 1, L of 0 1 equal to 3 4. So now the question is, can we find the linear transformation using this information? Answer is yes, we can. So how to construct the linear transformation? Since we know any vector x comma y in R2, and this is the basis 1 0 and 0 1 is basis for R2, right? Belongs to R2, and this set is basically basis, right? Okay, so you can say that since this is a basis for R2, okay, so it contains in R2, and since it is a basis, so every member of this vector x comma y can be written as a unique linear combination of the basis vector x comma 1 comma 0 plus y 0 comma 1, right? And since L is linear, you can apply L on it, right? L on it both side. When you apply L on both side, you will find since L is linear, again x times L of 1 0 and L of y times L of 0 1, and that is nothing but these values are given already, and you just add using component wise addition. So we have constructed the linear transformation, and this linear transformation is unique, right? Using the base action on basis element. Okay, so if we find another example, find a linear map from L from P2 to P2. So dimension of P2 is 2 plus 1, that is 3, right? N then n plus 1, so 3. And the action on basis element is given as L of 1, L of x minus 2 equal to x square. Now, can we construct the linear transformation? Answer is yes, if this forms a basis, right? So if you see this set 1, x minus 2 and x minus 2 whole square is linearly independent and hence forms a basis for P2, right? Because the number of elements are maximal linearly independent set. The number of elements is equal to 3. So this maximal linearly independent set forms a basis, right? So any polynomial which looks like a form ax square plus bx plus c in P2 can be rewritten in terms of this basis, right? So once you write in terms of basis, then you have to solve the system of equations, right? And then after solving this, you can collect the coefficient, and these all are the your coefficient which you have to figure it out, right? And these all are done very much while solving the system of equations, right? So assume you can solve this step. So now applying L on both side, L on both side, right? So using linearity of L, alpha L of V, right? So this is going to, these values are given to you. So you just plug these values, substituting the given values, right? And then you can solve the, after simplifying, your linear transformation will be this. Okay, so now let us see, we will generalize this. So theorem v1, v2, vn be an ordered basis for a given vector space V, and W be a vector space. Let W1, W2, Wn be any n vectors in W. Then there is a unique linear transformation L from V to W such that L of V1 equal to W1, L of V2 equal to W2, and so on, L of V3 equal to W3, and so on, L of Vn equal to Wn. or in other words we can reframe the given statement again. Let V and W be two non-trivial vector spaces and dimension m and n, right? We can go for any dimension here. Okay, so the proof we did for Rn to Rn. Now we are generalizing the result from Rn to Rm. So B is a ordered basis V1, V2, Vn, and W has ordered basis, let's say C, W1, W2, Wm, right? Then L is a linear transformation from V to W, right? Then there is a unique M by N matrix, let's say B to C, such that ABC is equal to operated on the V, which is written as the coordinatization of B is equal to L of V of C for all V is in V, right? That means that means ABC times of the coordinatization of V with respect to B gives the coordinatization of L with respect to C, right? Furthermore, we can say that for I equal to 1 to n, ith column of ABC is the equal to the L of V of I on C, right? So here you can see several such matrices. L operated on V1, V2, V3 is going to be V1, V2 minus V3, and then the transform matrix. So here the important point here, you can note that here we are finding A, B, B, right? Means B is a standard basis, right? A standard basis. So A, B, B, all of them, right? So standard basis 1, 0, 0. So 1, 0, 0. So first column, right? You can just assign first column and then 0, 1, 0, second column, and the third column 0, 0, minus 1. So life becomes easy when standard bases are given, right? And life become measurable when standard bases are not given. Then we have to find the coordinatization, and we know the method how to find the coordinatization from one basis to another basis. And only changes with the linear transformation is we have to reach to the other domain and then see how the basis can be calculated, right? So these all are some examples you can see, right? Dilation matrix, projection matrix, and rotation matrix through angle theta, and shear matrix, right? These are the matrix of transformation. Okay, so now we have to see a very important ingredient here. Let V and W be non-trivial finite dimensional vector spaces with ordered basis B and C respectively, and let L be the linear transformation with respect to matrix BC, right? And suppose D is another ordered basis for V and W, then P is a transition matrix from B to D, and Q is the transition matrix from C to E. Then ADE for L with respect to the basis D and E is given by, right? How do we know? If you see, before going to proof, what we do here is we can find this is a B, V is a vector space, and W is another vector space. So here B given, here C given, here D given, here E given. So B to C, right? If we find a linear transformation B to C, that means coordinatization we have to do. How do I find the coordinatization? So here A, B to C. It means that you have to allocate A, B, B to C. It means that this matrix is coming from coordinatization of You see here, we want B to C. B to C. That I have already discussed in coordinatization video, but again I'm explaining you. So write C vectors here as column, right? And you have to write L of, here important point is L of V1 and so on, L of Vn, right? With respect to basis of this you have to write here. Image will come basically here. And then apply RREF on it, and then whatever the matrix you will get, let's say IN, then this matrix will be your ABC, right? This is already we have done. Only here in matrix of linear transformation, you have to write this image of your basis vector B with respect to L. Okay. So now what exactly it has happened? A, B, C. Now similarly A, D, E, you can also figure it out. A, D, E. Now the question is, we know the coordination B to D. Coordination from B to D, we say, let's say P is a transition matrix from B to D, and you know how to calculate B to D already from the coordinatization. B to D means you have to, because you are not going to the transform domain. So B to D, how you will calculate B to D. So B to D means you have to write D columns, right? And you have B columns, right? And apply RREF, and to get this identity type matrix, and then write this side will be the P is basically here. P is basically here. You can say that A, B, D, right? B to D is nothing but here P I'm saying. Okay. Similarly, here if you see the matrix from C to E, we can also figure it out from C to E. So you have been given C already in W and E already given. So you can always find the coordination from C to E. So this is, let's say we can say that Q. So we need to find out this root from if you see, we want this root. We want this root can be understood like I can go from this route. If you see, I can go from this route and this route and this route. So I want to go from D to E. So I have two paths. One path is this cyan color one, P, from this to this, D to B, then B to C, and then C to E, right? Now, since we have the matrix of transformation from D to B is P, so this route will be P inverse, right? Reverse order. So I want to write DE, so we can say that DE can be written as Q, first Q, then ABC, then P. So DE can be written as Q, then ABC, then P inverse. This is a very simple actually, right? And this is very interesting as per the coordinatization we have done so far. Okay. So now let us see the proof. So for all V in V, A of BC, A of BC, if you see from the figure, A of BC, A of BC will transfer any vector V in B written as a B coordination. When you multiply this, you will reach here, right? So which will be nothing but your L of, using the linear transformation, L of V with coordination of C, right? With respect to C vector we are writing C basis, right? And then if you pre-multiply Q from both side, then you will still Q, you are going to multiply Q, so you are still in the same domain, but the basis changes from C to E, right? Because Q is going from C to E. Okay, so what had happened here, the left hand side is as it is, but right hand side changes to E basis, right? Because Q is a transformation from C to E. Okay, and then if we post multiply P inverse, right? Post multiply pre inverse. What had happened is post multiply P inverse. So what does had happened here is, rather than B, you see, post multiply if you do, then this will change, B will change to D coordinatization, right? So here D coordinatization, and this is going to be E coordination, right? So now this is how you can prove. However, D is unique matrix, right? For all V is in V. So we can write AD equal to Q BC P inverse, right? So this is how the transformation can be seen. Any vector B, any vector V can be written as a linear combination of the basis vector B. So B coordination, and then if you see here, P is a transition matrix from this to this, and Q is a transition matrix from C to E. Then ADE can be obtained using this path, right? So we want this path actually. So for this path, we need the inverse P inverse, and this path is A, B, C, and this path is Q. So Q, A, B, C, and P inverse, right? Okay. So let us apply the theorem on some problem. Okay. So let us do this problem. Find the matrix ADE for the given linear transformation L from V to W with respect to the given basis D and D, right? By first finding the matrix for L with respect to the standard basis. So they are going to give you the standard basis B and C, right? And for your V and W, and they're also giving you two different bases D and D. Then they're asking find the matrix of transformation from D to E. So the whole problem is like that. You have been given V and you have been given W. So there is a linear transformation L. Okay, they have given a linear transformation, and B and C, they are saying that assume these all are the standard basis, right? R3 to R3 standard basis. Standard basis for R3 is E1, E2, E3, right? So where E1 is basically 1, 0, 0. E2 is basically 0, 1, 0. And E3 is basically your 0, 0, 1, right? So this is the basis for V and W from R3 to R3. So this is the standard basis, right? So first they are saying that find the uh, matrix of transformation ADE, right, for the given basis D and DE by first finding the matrix L with respect to the standard basis B to C. So A, B, C, we have to use a standard basis. D and E, they have already given to you two different bases, not standard as well. So you have to find this A, D, E using the same theorem, and C, you have to find Q, and you have to find P inverse, right? And then do multiplication. This is our complete problem. Okay. So A, B, C. How do we find A, B, C? Let us see. So since the linear transformation is given by this, so and the standard basis already we know standard basis vectors are E1, E2, E3, right? And are transformed. So the transformed vectors are LE1, LE2, LE3, right? So now to find the matrix L, the matrix for the given linear transformation L with respect to the standard basis, so which is going to be A, B, C. So how do you find A, B, C? So you see here B, 2, C you want to know, but if you see your V is this, W is this, very easy, try to understand. And this is L is a linear transformation and B is the basis, right? And here C is the basis for W. So what had happened here is I want to find basically here, if you see the matrix of transformation from B to C, it means that you have to write C, C and L of, because now if you reach from here to here, so what is happening here? L of B you have to find out, right? L of B, because L operated on B. So what had happened? C columns, C columns, C vectors in column wise you have to allocate, okay? And augmented matrix L of E1, L of E2 and L of E3 you have to write as a column vector, right? Now what had happened here is the important part for you is that luckily this C columns, C column is standard basis E1, E2, E3, right? So they have given you this is C. C is the standard basis, right? So what you can do 1, 0, 0, 0, 1, 0, 0, 0, 1. So we are finding the matrix of transformation from B to C. So we have written C and then L of image with respect to B basis. So image with respect to B basis can be obtained using the linear transformation, right? So B basis is this. So L of this vector, right? And this will be written as the column, first column, second column, third column in the right hand side. So minus 1, 0, 1. So you can write here minus 1, 0, 1 and 1 minus 1, 0, 0, 1, 1. So this is how the coordinatization works. So now you apply RREF on this to get a new matrix. So, but if you see this, this is already in RREF form. You see here because of the standard basis C. So this is already RREF. Okay. So now if this is an already RREF, then what you have to do? I3 and whatever the matrix will come here will be nothing but BC. So just rewrite this matrix, pull back and write. Okay. So the job become easier when standard bases are given. Okay. So this is what first we have obtained the ABC. Okay. Now the second part is that we have to find the transition matrices P and Q with respect to the standard basis. Again, if you see that the transition matrix P inverse from D to B, if you see here in this map, so D and E. So we have to find the transition matrix P inverse, right? So P inverse, so transition matrix, how do you find? This is again coordinatization will work here. So you want to find D to D to B, right? D to B means linear transformation not used. You are here in this domain, right? So just write the B vectors as column and then D vectors as column. And since B is already standard basis 1, 0, 0, 1, 0, 0, 0, 1. And then D vectors as column, D matrix is already given to you, right? D 5 minus 3 1, 5 minus 3 1, 1 0 1, and then last vector is 1 0 1, 1 minus 1 1. So 1 minus 1 1. Now since this is again the standard case, this is I3, right? Already RREF reduced form, and then this becomes your P matrix, right? P inverse matrix. P inverse matrix from D to B, right? So P inverse can be easily obtained. If you see, P inverse can be easily obtained by using this. And RREF is not at all applicable here because it is already in the RREF form, right? So P inverse is obtained, right? Now we have to go to find the Q. Q is nothing but from C to E. C to E means, again if you see here, C to E. So for finding C to E, you have to write this matrix C to E, transition matrix Q from C to E, right? So Q from C to E means if you see the pictures, right? So if you have this V and this W, right? And this is L is a linear transformation. B and C are the standard basis. D and E are your D and E, D and E be the given basis. So now if you see here, this A, D, E, and now we are in the process of calculating Q. Q is a transition matrix from C to E. C to E. C to E means you have to construct the matrix with respect to E. E basis vector is already given like this. So E and C is the standard basis. So C you can write and perform RREF. Perform RREF on it, right? Because C and B are standard basis given to you. Okay. And already we have seen P inverse, and we have already calculated A, B, C with respect to standard basis, right? So now if you apply RREF, you can refer my second video how to find the RREF. Then we have obtained the RREF, and then we got this matrix. So we can pull out this matrix as become Q. So now we have to apply the simple formula. ADE is equal to QABC into P inverse. So just you write three matrices which we have already obtained, and then you will find this ADE. ADE can also be figured it out. Already you have been given ADE we want, then you have been given already D. You see E first you have to write. D to E means D to E means first write E basis vector, write E columns, and here you write D columns, right? And then perform RREF. After applying RREF, you will get to here D column with the image of D column, basically image. First you plug the vectors, then image of D vectors. Here you have to write V1, let's say, and so on, L of Vn, right? So this is very important, image of D column, right? So this is very very important, and that you know how you have figured out before, because linear transformation is given, then you just apply. Let's say D is consisting of three basis element, v1, v2, v3. So L of v1, L of v2, and L of v3, you have to find out. So that you write in this column, right? So here image column, right? You have to write image column D, and then you can write E column and apply RREF and then get your matrix like this: identity, and then here A, D, E, which can also be figured out using this. Okay. So now if you see the special, what is the special case? If V and W are same, right? Suppose B and C be two order basis for V, then ACC is equal to P ABB and P inverse. In this case, we can say that the two matrices are similar, right? So you can easily figure it out if you have V and if you have V again, right? Then you can always find using this linear map, right? So here what had happened is B and C, B and C. So from here to here, L is a linear transformation. So A, B, B you will get, and from here to here you will get Q, and from here to here you will get P inverse, right? And then from here to here you will get ACC. So ACC can be written as Q, A, B, B, and P inverse. So here Q is nothing but basically P, right? So which can be written as P, A, B, B, and P inverse, right? And ACC. So this is another important result, right? So this is very useful when we are supposed to find the similar matrices. Okay. So now another important result: V1, V2, and V3 be three non-trivial finite dimensional vector spaces with ordered basis B, C, and D respectively. Then if it means you have a linear, if you have a vector space V1, if you have a vector space V2, and if you have a vector space V3. So L is a linear transformation from L1 is a V1 to V2. L2 is a linear transformation from V2 to V3. This is having basis B, C, and D. So now the composition map from here to here. So L composition L1 is a linear transformation from V1 to V3. This is what this theorem is nothing but this matrix is A, B to C, right? And this matrix is A, C to D, right? So A, you can say that B to D is nothing but the product of A, C, D, A, B, C, reverse order, right? This to this, this to this. So from here to here means this and this, right? So now we can see example based on it. So given matrices A, B, C. So here in this problem, I just wanted to give you the how this theorem works. But I could have also given you B and C and D and then ask you to construct B to C. And then again, you have to perform this matrix from A, B to C, means you have to write the A, B to C, B to C. If you are going, then you have to find out this transform domain and then write this C column and then write like I want to know A, B, C is nothing but you can just write the matrix, augmented matrix. Here you write the C columns because B to C you are going, right? B to C. So C column first you write here all the C column, whatever the C column vectors are given, basis vector, and then write here L of V1 and so on, L of Vn, where B V1, V2 and so on, Vn is a basis B, you can say, right? So image you have to write and then apply again the perform the RREF because linear transformation is given. Then in that case I have to give you the linear transformation and then you have to apply RREF and then find this matrix of such forms, right? And then here you can write your matrix A, B, C. All right, this is a very simple actually. Okay, so here rather giving all the calculations, I'm just going to use how theorem works. So already I am going to give you the ABC matrix and ACD matrix. Now I want to compute A from B to D is a composition transformation L composition L2 composition L1. That is nothing but this because matrices are given. So ABD is nothing but product of these two transition matrices, right? Transform matrices. So when you do product, you will get, you know, this matrix, right? Okay. So another problem, find the linear transformation L from V to W. For given linear transformation LV from W, find the matrix L with respect to the standard basis. So this is again very simple cases. So you have to use standard basis only, V and W. So standard basis, you know, E1, E2, E3. So you have to find the image and then you have to construct the matrix. How you construct the matrix? And here again standard basis E1, E2, E3, right? Is the basis for W and this is a basis for V. So you have to construct L of V1 and so on L of V3 and here let me write very clearly. So here you can say that L of V3 and L of V3 is nothing but your E1, E2, E3, right? So here you can write rather than this you can write L of E1, L of E2, L of E3. So and you can write the basis for your W. So E1, E2, E3 as column vector. And no need of performing RREF because this is already the standard basis. So you just pull out this matrix after the transformer. So what is the idea here? 1, 0, 0. If we plug here, I'll get here the new vector and then this new vector will be a column here, right? And similarly we can find for all of them. So now you see here standard basis ABB of L can be found by computing these three and E1, E2, E3 is the standard basis. So this vector, and this vector. So matrix can be directly written as the column of these three vectors, right? So ABB can be written as this matrix, right? Another problem, let L from R3 to R3 be given by this map. What is the matrix for L with respect to the standard basis for R3, right? And what is the matrix L with respect to the basis C? And then third part, what does your answer to part B tells about the vectors in C and explain. So now you know what you have to do. Standard basis, job is easy. Now different basis, job becomes little difficult because you have to perform RREF, but it depends upon where to where you have to figure it out, right? So now to find the standard basis ABV of L, we determine LE1, LE2, LE3. So since linear transformation is already given, right? So you know already this standard basis, so you have to allocate the LE1 to LE3, and here standard basis 0 1 0 0 1 0 0 0 1, and this is already RREF. So whatever the column you will get, the image you will get, just pull back in your matrix A. This is your standard basis. So 0 4 minus 1 0 4 minus 0 minus 4 1 0 minus 4 1 minus 2 3 minus 1 minus 11 4 minus 4. So this is your matrix part 1. Part 1 says find the matrix with respect to standard basis. Now what is the matrix for L with respect to C? So they are asking A C C basically, right? So ACC can be obtained using the C columns, right? And the transformed C column, right? L of C1, whatever the column vectors are, you have to figure it out and then perform RREF. So now part this, okay? So to find the matrix L with respect to C basis, we can use the previous formula, right? Either you have to find out using this method, right, which we know, but since we have already calculated b b, so we want to use the previous result, similarity of matrices. So now we know that ACC can be obtained using PABB P inverse, and where P inverse is a change of basis matrix formed by columns of C, right? So if you have the picture again, if you have the picture again, like if you see B and again B, again B, again B and C, C. So if you see C to C, A, C, C can be obtained as B to C is P and C to B is P inverse, right? And this ABB. ABB can be obtained as columns of B and then transformed image with of L with respect to B, right? And then perform RREF and get the result. Okay, so now the question here is P inverse. P inverse from C to B, C to B, C to B, right? C to B means you have to first write the B columns, and B columns are standard basis. Look at it. Augmented C with respect to the image of the given basis, right? So you have been already given the your this vector you have to plug, right? These vector you have to plug in your linear transformation. So 1 0 1 minus 1. So when you plug 0 1 minus 1, uh, then what had happened here is C to B. C to B means the same you are going to calculate. C to B means simply you write the columns, right? So what are the columns of C? C means columns of C means your 0 1 minus 1 1 0 minus 1 1 minus 1 1. So the due to the beauty of your from same space without transformed one we are doing. So P inverse can be obtained from C to B. C to B means first columns of B, and columns of B are the standard basis, and columns of C, C is already given to you. So just assign as a column, and then in that case what had happened here is you are going to calculate the RREF, but no need of calculating RREF because this is already in RREF form. So just pull out this matrix, okay, and this is your P inverse. So P inverse is calculated. Now you know how to write P as well. right? To compute P, you can use the same way, right? But from B to C, right? From B to C, if you do, then you will find P means P matrix means B to C. So C columns are already 0, 1, minus 1, 1, 0, minus 1, 1, minus 1, 1, right? And then B column already standard basis. So in that case, this is not in RREF. So apply RREF. So you know how to apply RREF to make the form like this. Identity and then here A, B to C, right? You got a point or not? And this is nothing but your P. Okay. So after applying RREF, you got this matrix. Okay. Or else you can, this is a singular, you can also calculate A inverse, a P inverse, and P inverse of inverse is going to be P. You can also do that. But here the purpose is using the change of coordinatization we are going to perform, right? So we have to stick to that one. Okay. So now once P is calculated, P inverse is calculated, PAB is calculated, we just do multiplication of these three matrices to get the final answer, right? Another, uh, the transform matrix is going to be here ACC is this one. This is the answer for part B. Okay. Now part C, the matrix ACC shows that the basis C does not consist of the eigenvectors of L as because of the fact that ACC is not a diagonal matrix. So see here, this is not a diagonal matrix, right? So what is a key observation? So if a basis consists of eigenvectors of L, then matrix representing L in that basis should be diagonal, right? But this matrix is not diagonal, so basis consisting of eigenvectors are not representing the basis for L, right? Matrix L. So now a diagonal matrix, what is the diagonal matrix? Has non-zero values only at the main diagonal, like this, right? And zero elsewhere. Okay. However, our computed matrix ACC contains non-zero entries at the off-diagonal entries, right? Off-diagonal entries are non-zero. These entries are non-zeros. You see, okay? So this is not at all a diagonal matrix. Okay. So in that case, since ACC is not the diagonal, the basis C does not consist of the eigenvectors of L. So this is our conclusion. So thank you very much. Thanks a lot.